All right, so this is section 6.3. We're talking about square root functions and square root inequalities. So the parent function for a square root function is f of x equals the square root of x. This is what the parent function looks like. And if we graph it, what is x allowed to be? Right, let's plug in 0. If I plug in 0 for x, the square root of 0 is 0. If I plug in 1 for x, the square root of 1 is 1. So 1, 1. Now, if I start to put in 2, that's going to get me a decimal. The square root of 2 is a decimal. So I'm going to skip to another number I know works out nicely. So it's 4. The square root of 4 is 2. So 4, 2 is a point on my graph. And then again, I'm going to skip to another number I know will work out nicely, 9, 3. Right, so I'm going to just put it out here. Now, what happens if we go to negative numbers? If we try to plug in x equals -1, right? The square root of -1 becomes I. We are not graphing imaginary numbers. This xy coordinate plane is a real number coordinate plane. So we are not going to be graphing any imaginary numbers here. So my graph cannot go any further left than 0, 0. So the graph will actually look like this. It will go forever to the right, but it comes to a hard stop at 0, 0 because we cannot have a negative underneath the radical sign. So the domain of our radical function is all real numbers, and then we can say x has to be greater than or equal to 0. Typically, people will just say x is greater than or equal to 0. They won't put the all real numbers part. So I'm okay with you guys doing that as well. The range of our parent function, look at the graph and see where all the y values are. All the y values are also above 0 here. Just looking at the graph and the table of values. Now down here, we have all the transformations that can happen to this parent function, and these things should look familiar to you. So we've got this red a value out in front. That a value does the same things it's done all school year with the other functions we've done. That a value tells us if there's a vertical stretch or compression. More specifically, if the a value is greater than 1, there's a vertical stretch. If the absolute value of the a value is less than 1, there's a vertical compression. You might need to add that into your notes. I'm not writing it on the screen. So rewind and hear it again if you need to. The a value also tells us if there's a reflection across the x-axis. So if the a value is negative, then we're going to reflect over the x-axis. So up here on the parent function, I'm just going to add in a pink negative sign, right? That's where the red a value would be. And what that would do is my graph would look like this instead, the pink, right? It would reflect over the x-axis. All those outputs would become 1, -1, 4, -2, 9, -3, right? So that's what that would do if you had a negative sign out in front of the absolute value. I'm sorry, in front of the radical. The next thing is the h and the k. Remember, the h is our horizontal translation, or horizontal shift is the word that I used. So it tells us to move either right or left. Remember, it's the opposite. So if you have x -4, then it would be 4 to the right. Our k value is our vertical shift, so up or down. And then this 1 over b, we've talked about numbers that are here. It's the multiplication inside. We're not going to dive too much into this, but the b value tells us about the horizontal stretch or compression. And remember, the way we taught it in a different section was we take that number that you see in that position and we do the reciprocal of it. So, for example, you might see this. So you see how this number 1/3 is in that position of the horizontal stretch or compression? So we said this was a horizontal stretch. And when we said by a factor of, we took that fraction 1/3 and we flipped it. The reason why you're flipping it is because you want this b value, right? And so that's what we didn't talk about it in this context when we did it earlier. I just told you to flip that number, right? Do the reciprocal of it. So we need the b value, and the b value is the reciprocal of whatever number you see in this position. So if the number is 4x, right, then this is a horizontal compression, and we would say by a factor of 1/4, right? You flip that number to figure out what the b value is. Okay. So that's all your stretches and compressions. This number, if there's a negative here, which we're not going to do that. Oh, are we? Oh yeah, we are. If there's a negative sign in this position, so meaning if there's a negative sign under the radical, then that is a reflection over the y-axis. So we will do that. Okay, so let's do some examples of graphing. So the first thing we're going to graph is h of x equals 2 square root of x plus 4. What we're going to do for each problem is we're going to graph using 4 ordered pairs. So for every question, Mrs. Inglay's rule is I want you to come up with at least 4 values in the table of values. All right, so at least 4 numbers in the table of values, 4 points. Even if they don't fit on the graph paper, you're still going to write down 4 ordered pairs. All right, then you're going to fit whatever you can on your 10 by 10 graph paper. Now, when you go to fill in your table of values, you want to find, right, the first dot where like this wave happens. This is the shape of a square root function. We want to find this point, right? That's the starting point. And the way you find that starting point is you set the radical equal to 0. Whatever is underneath the radical sign, you set that equal to 0. You want, because that's the smallest the number under the radical can be, right? This space here, the smallest number it can be is 0. So that's where we want to start. So I'm going to take what's underneath the radical, and I'm going to set it equal to 0 and say, okay, this radical will be 0 when x is -4. Then I'll plug in -4 into the function. So square root of -4 plus 4 is 0, and then multiply by 2. So my output is -4 is 0. So that's my first point. Notice when we say describe the transformation, we would say this has a horizontal shift left 4. So it makes sense that this is where my first dot ended up. Now, what's the next nice number we want to have underneath the radical, right? We don't want decimals. We want nice integers. So 0 was the first nice number under the radical. What's another nice number we would want to have underneath this position? So 0 was the first one. It would be nice if we had the square root of 1. So I'm going to take the radical, and I want that radical to be 1. So what does that mean x would be? -3, right? So -3 plus 4 is 1. The square root of 1 is 1. 1 times 2 is 2. What's the next number I would want to have underneath my radical? So 0, square root of 0, square root of 1, square root of 4. I want that radical to be equal to 4. So I'm going to take that radical and set it equal to 4. So my next x value would be 0. Plug in 0 into h of x. And you should be getting 4. Let's do one more. We want 4 points. So the next number would be 9. We want to take that radical and set it equal to 9. So the next nice x value we're going to work with is 5. plug it into the function, and you should get an output of 6. And then I'm going to draw my graph. Right, so let's describe the transformation. I'm not going to write it, so just listen to it vertically. The transformation would be horizontal shift left 4, vertical stretch by a factor of 2. If I graph the parent function looks like this. Can you see that difference? Can you see that it shifted left 4 and it also vertically stretched? That wave became a little bit taller, right? More vertical. And then let's state the domain and range. So the domain is all the x values have to be greater than or equal to, right? What's our first x value? Our first x value was -4, and then we graphed it to the right. So everything has to be greater than -4. And what about my range? All the y values are above. What's the smallest y value we used? The smallest y value we used was 0. So all the y values are above 0. So when you're making your table of values, these numbers you can figure out by doing these 4 equations. Set it equal to 0, set it equal to 1, set it equal to 4, set it equal to 9. Right? All my perfect squares. If you wanted another one, you would set it equal to 16. Sorry, that's the example we just did. All right, so let's start this one by describing the transformation. Go ahead, pause the video, see if you can describe the transformation. So, describe the transformation. We've got a horizontal shift right 3. We've got a horizontal stretch by a factor of 4. And we've got a vertical shift up 1. Make sure you're using that correct terminology. So now we're going to create a table of values. Take the thing that's underneath the radical, set it equal to 0, and figure out that's going to be your first x value here, which is 3. Then take it, set it equal to 1. That'll get you your next x value. Set it equal to 4, set it equal to 9. Go ahead, pause the video and see if you can get all those x values. So these should be your x values that you're getting. Those will get you nice perfect squares under the radical. Now go ahead, pause the video and go substitute these numbers into the function and figure out your outputs and then graph it. And these should be the numbers you're getting. Now, we don't have to graph all the way to 39, 4, but we're just going to graph what we can fit on the graph paper. And so it looks like this. Do you see the vertical shift and the horizontal shift, right? This starting dot went to the right 3 and up 1. And can you see the horizontal stretch, right? So horizontally from left to right, this became like, if I took a piece of Play-Doh and pulled it left and right, it becomes a little bit more elongated left and right. Domain, x has to be greater than or equal to 3. Range, y has to be greater than or equal to 1. Maybe you've picked up on the trick that this first ordered pair helps you with the numbers for your domain and range. The only reason this would change is what we're about to do next. If you reflect, then these inequality signs could change, right? Maybe we're going below those points instead of above those points. Right, and we're going to try, I think, one more example. So describe the transformation. we've got a reflection over the y-axis, which means my graph is going to go to the left. That's what a reflection over the y-axis means. I also have a vertical shift down 2 units. So take the thing that's under the radical, set it equal to your perfect squares, and figure out your x column. Right? Pause the video if you haven't done so already and go figure out your y column. And then graph. So do you see, as you're graphing, you should see the transformation that you stated. It was a vertical shift down 2 and reflection over the y-axis. So you should see that. It's a good check to make sure you're doing it right. Your domain, your domain, we're not going to do domain right now. Let's pause on that. The reason is because I just realized, and I'm not paying very close attention, Miss Ingley, is that we changed this to an inequality symbol. So notice I've just graphed everything the same way I normally would graph. And now what we need to do is we need to think about the inequality symbol. How does an inequality symbol change our graph? What I just graphed was an equation. I was totally not even thinking about the inequality sign. So I graphed the equation. Now, what does the inequality sign do? Think back to what we did for quadratics. Think what you did back to linear functions. When something was an inequality, how did that change the graph? 2 things. Number 1, you're thinking solid or broken line. And number 2, you're thinking there's shading involved. So because this is a greater than symbol without the equal to sign, this is going to be a broken line. Now, our starting point, 0, -2, we also need to graph that as an open circle because we want to make sure that that point is not included. These I'm doing as closed circles because the line, when I draw it, a broken line, that broken line is showing me, like, don't include these points. But that first circle, it's helpful to show that it's, an open circle is useful. And now I need shading. I am either going to shade above the square root or I'm going to shade below the square root. So it's going to be one of these. The question is which one. Notice that I did not shade over here at all because my domain is that the x value has to be less than 0. I cannot go to the right of that starting dot. If I do, you go to imaginary numbers, and we definitely don't want to do that. So how do I decide if I'm going to shade the blue or shade the pink? We're going to test a point, either in your head or on paper. I'm going to do it on paper. So I'm going to test a point. You want to test something either above or test something below. Now, I would not test 0, 0 here because 0, 0 is like on that domain border. So we want to pick something that's clearly above or below the actual graph. So I'm going to do -4, 2. Right, so -4, 2 is my test point. Right here, this is what I'm testing. So I'm going to take it and I'm going to substitute it in to my function. And it is true. 2 is greater than 0. I got a true statement here. So what that means is that my ordered pair that I chose, -4, 2, is a solution. And remember, all the shading needs to be things that are solutions. So my test point was true, so I want my test point to get shaded. So the blue shading was the correct shading. If my test point was false, I would have wanted to shade below the graph. Square root functions with inequalities, pretty straightforward. Greater than, we shade above it. Less than, we shade below it. If we have an equal to sign, all that changes is that we have a starting circle that's a closed circle, and then a solid line when we connect the dots. But test point is good just to verify, make sure it's a good double check, but greater than is above, less than is below. All right, guys, I think that's good. If you have any questions, reach out to me and make sure that you ask them in class. Thanks.